Hello, in this lesson we will learn about formal reasoning in Euclidean geometry. The learning goals for this lesson are: understand what a conditional statement is and identify its hypothesis and conclusion, learn how to use a truth table for conditional statements, learn the concepts of postulates and theorems, differentiate between Euclidean and spherical geometry. Let's start with this concept of conjecture and counterexample first. A conjecture is a statement that appears to be true but has not been formally proven. Basically, it is an educated guess that is based on known information. For example, here we have different birds: a sparrow, eagle, robin, etc. And we realize that all of these birds can fly. So that would be our conjecture. We see this information, right? We see this phenomenon that they fly, and we come up with this conjecture. A counterexample is a specific example that shows that a conjecture is not true. If we observe a penguin, we realize that a penguin cannot fly. So that would be our counterexample. Penguins are birds and cannot fly. Therefore, this conjecture that all birds can fly is wrong, as proven by this counterexample. Okay, so basically a counterexample is any example that will prove the conjecture wrong. Conditional statements, also known as if-then statements. This is an example of a conditional statement. You have the if part, you have the then part. Here, if I study, then I will pass the test. The I study part is the hypothesis. The I will pass the test is the conclusion. Those are the two parts that a conditional statement has: a hypothesis and a conclusion. If I study, then I will pass the test. So if P, then Q. P represents the hypothesis and Q represents the conclusion. In this particular example, P is I study and Q is I will pass the test. If P is true, then Q is true. Okay? So if the hypothesis is true, then the conclusion will be true as well, according to this conditional statement. If I study, this is true, then I will pass the test. And this is the way that we represent in mathematics this type of statements. We put P, an arrow, and Q. This means if P, then Q. Again, in this particular example, it would be if I study, then I will pass the test. The truth value of a conditional statement is whether the statement is true or false. If a conditional statement could be true, then the truth value of the statement is considered true. Very important. So even if there is a possibility that that statement is true, then the whole statement is considered as true. Now we're going to work on the truth table for this conditional statement. Again, we're going to use the same example as we gave before. I study, I pass the test. This is the hypothesis, this is the conclusion. So this table will contain the truth value for P, for the hypothesis, the truth value for Q, for the conclusion, the interpretation of P and Q, and here is our conditional statement. If I study, then I will pass the test, which is P arrow Q. That's how we represent this conditional statement. Let's start with the first set of values. If P is true and Q is true, then I study will be true, right? I studied. I passed the test will be also true. I passed the test. Okay? So that's what happens, or what happened. I studied and I passed the test. Therefore, this statement, if I study, then I will pass the test, is true because I studied and I passed the test. And that's exactly what this says. If I study, then I will pass the test. So this whole statement, this conditional statement is true if this situation, these two are true. What happens is that if the hypothesis, the P is true, but the Q, the conclusion, is false. So basically, I studied and I didn't pass the test. Then this statement is false because this statement says, if I study, then I will pass the test. But I studied and I didn't pass the test. Therefore, this statement is false. Now, what happens if the hypothesis, the P, is false and the Q, the conclusion, is true? Basically, I didn't study and I passed the test. So that doesn't really affect this statement. This statement, this conditional statement says that if I study, then I will pass the test. But it doesn't say anything about if I didn't study, right? So basically, this statement is not affected by this situation, okay? So that's why if this is false and this is true, the whole conditional statement is still true, right? If I didn't study and I pass a test, that doesn't affect this because this only cares if I study, not if I didn't study, okay? Same thing. If I didn't study and I didn't pass the test, so if both of them are false, that doesn't affect this statement because, again, this statement only cares about the situation when the first one, the hypothesis, is true. If I study, if this is true, then this happens. But if I didn't study, it doesn't say anything about the situation where I didn't study. Therefore, this statement still is true if the hypothesis is false. So this still will be true. Okay? So in these two cases, where the hypothesis is false, the statement is not affected. Therefore, it is possible that I didn't study and I passed the test, therefore true. It is possible that I didn't study, I didn't pass the test, so it's true. Okay? The only case where the statement, this conditional statement, is false is when it contradicts the statement. Basically, if I study and I didn't pass the test, that contradicts the statement. If I study, then I will pass the test. That's why this is the only case where this statement is false. Now let's go into postulates and theorems. These two concepts are important in this lesson. A postulate is a statement accepted as true without proof, often considered self-evident. For example, a straight line segment can be drawn joining any 2 points. So if we have 2 points, we can draw a segment. That's a postulate. You don't need to demonstrate or prove this to be true because it's obvious, it's evident. So that's what a postulate is. It's something that is so obvious, so evident, that you don't need to prove it. Everybody accepts that as true. A theorem, on the other side, is a statement that has been proven to be true through a logical sequence of arguments called proof. So, for example, the interior angles of a triangle sum to 180 degrees. That's a theorem, okay? It's not obvious that the three interior angles of a triangle are 180. That's not obvious for anybody. So you have to prove that. At least they prove it, and now you trust the people who prove this. Okay, here is the proof, right? We're not going to go into the details of how to prove that, right? But the point is that a theorem needs to be proven. It has been proven, and that's why we can use it in mathematics. Whereas a postulate doesn't need to be proven because it's kind of self-evident, it's obvious. Okay, that's the difference. Now, let's go into this concept of geometry, the general concept of where geometry started. Euclid of Alexandria was an ancient Greek mathematician who is regarded as the father of geometry. So basically, Euclid was the most important person in the beginning of geometry, the one who created the postulates and theorems that are the basis for modern geometry. He wrote a book titled The Elements, where he used a small number of postulates to systematically prove many theorems, developing what is known as Euclidean geometry. Now, let's go into some of these postulates. First, let's go into this concept of a linear pair. A linear pair is a pair of two adjacent angles that form a straight line. So, right here, we have two angles, PSQ and QSR. And these two angles are a linear pair because they are adjacent and they are forming a straight line, right? They are on one side of the straight line. So the postulate, the linear pair postulate says that if two angles, like these two, form a linear pair, then the angles are supplementary, right? So if you add this angle and this angle together, it has to be 180 degrees. So that's basically self-evident, obvious. That's why this doesn't need to be demonstrated, right? You just see that these two angles are on one side of the line, therefore you know they are 180 together, okay? So that would be the linear pair postulate. Now let's go into the segment addition postulate. It states that if point B, right, let's draw point B, is on AC, is on the segment AC, between the points AC, then AB plus BC equals AC. That's also obvious, right? That if you have two segments together and you add them, that's going to equal the value of the longer segment, right? AB plus BC equals AC. That's the segment addition postulate. Now, this is the last postulate we're going to analyze, the angle addition postulate. It states that if point D, let's draw the point D, lies in the interior of the angle ABC, this is ABC, so point D is in the interior of the angle ABC, then the angle ABD, this will be the angle ABD, okay, right there, ABD, plus the angle DBC, this is DBC right here, equals the angle ABC. Okay, so these two angles, this green and this pink angle together equal the black angle here. Okay, that's why it says, right, ABD plus DBC equals ABC. And again, that seems to be obvious, self-evident, that these two small angles equal the big angle there. Okay, now that we have explained those concepts, we're going to go into the comparison of our Euclidean geometry, which is what basically we're studying, comparing with other types of geometry. Euclidean geometry deals with flat two-dimensional spaces, while non-Euclidean geometries describe curved spaces like spheres or saddle shapes. So here we have an example of Euclidean geometry, right? It's just a right triangle on a plane, right? This is a plane and we draw a right triangle there. Now, if we are working on the surface of a sphere, we're going to be using spherical geometry. Right there you see that we are drawing the equivalent of this right triangle that is on a plane, but this time is on the surface of a sphere. And here the properties are going to be different. You see that the angles are going to be bigger. Together, these triangles are going to be more than 180, as it is the case in plane geometry or Euclidean geometry. Now there is also hyperbolic geometry, right? This is a saddle shape here. And this triangle, the angles together are going to be less than 180. We add the three interior angles of this triangle. So basically, spherical and hyperbolic geometries work on different surfaces, not planes, and therefore the properties are going to be different than Euclidean geometry. Another way to describe the differences between these geometries is to consider two lines in a plane that are both perpendicular to a third line. So in Euclidean geometry, when you have two lines and there is a third line that is perpendicular to both of them, we know that these two lines are called parallel lines. Okay, they are parallel to each other. But in hyperbolic geometry, the lines curve like this, away from each other. Therefore, in this geometry, these two curves, which they call lines, are going to be parallel to each other. But since these are curves, we can draw more. We can draw another one here, another one here. In other words, here, if you have a line and you draw a perpendicular to a given point, let's see this point, there's only one parallel line to this line. You cannot draw more than one parallel line through this point. But here, you have a line and you have a point, and you can draw one parallel line to this one, and you can draw many other parallel lines to this one. So in hyperbolic geometry, you can have many parallel lines that pass through a single point, different from the point of the initial line that you are using. In elliptic geometry, the lines curve toward each other and eventually intersect. So you see these two lines here, they are going to intersect each other. Therefore, there are no parallel lines. Because all lines intersect, there are no parallel lines. Because the concept of parallel line implies that the lines will never intersect each other. In spherical geometry, which is again a different type of geometry, triangles have different properties, right? For example, this triangle here has 390 degrees. So you add the interior angles is 270, 90 plus 90 plus 90 to 70. So you see the properties in spherical geometry are different from those properties in Euclidean geometry. Okay. Finally, in spherical geometry, lines are gray circles. What are gray circles? This is a sphere. This one is a small circle. You see, if we take a plane and we cut this sphere, we will generate a circle here, which is not the biggest possible circle we can generate in this sphere. But we take a plane and we cut it through the middle, then that will be the biggest possible circle, which is called the gray circle. Okay? So basically the gray circle is like if you are cutting slices of an orange, the biggest possible slice that you can get, right? It will be this one, the one that when you cut it in the very middle, right? So the gray circle is the largest possible circle that can be drawn on the surface of a sphere, right? The center of the sphere would be at the center of that gray circle, okay? Now, in spherical geometry, if you choose any 2 points on the sphere, and you join them together, they will generate a great circle. So that's why in spherical geometry, lines are great circles. So it doesn't matter what 2 points you choose. You can choose 2 points, point here and point there. If you join those 2 points, okay, and you go all the way around the sphere, there will always be a great circle. That's why in spherical geometry, lines are great circles. Well, that's all we have for today. Thank you very much for the attention.